Have you ever imagined a virus 100 times more destructive than COVID-19? In the last century, there was a pandemic called Spanish flu, which murdered 20 to 40 million of people the first year, and some sources say that even 100 million at the end of the second year. This means more than 5% of the global population. Making a comparison, COVID has claimed 970,000 people till today, and 650,000 are killed every year by seasonal flu. Sadly, these deaths seem to have been internalized nowadays in our society. But this explains the international effort to fight this pathogenic and the huge amount of money that implies the research, prevention and protection of population, because if a new outbreak appears, the results will be fatal. In contrast to COVID, the main problem is that we cannot produce a vaccine, because the virus is quite different each year. A viral protein named RNA polymerase is responsible of this variability, a tiny motor that copies the genetic material. My name is Carlos Rodriguez, and I've been working these last years in my thesis project, based essentially on understanding these molecular models. Borja Ibarra's lab is pioneer using the optical juices technique. This technique was rewarded in 2018 with the Nobel Prize in Physics and allows us to trap nanoparticles with lasers in order to manipulate them. If we could open the capsid, we could see that the genetic material is divided among 8 different segments. Each one owns one polymerase. When the contents are released into our cells, the motor starts to work. It goes through the viral RNA making an identical copy. Then, from a model we will get billions of sons which are ready to infect more cells. The interesting point is that any motor in nature fails. When the motor is not able to copy exactly an element called nucleotide, we obtain a mutation. The special feature of the flu is that this motor doesn't have a mechanism for correcting them. Thus, the son and his mother will be pretty different, and 1 year later, the number of cumulative errors along many generations will make virus get immunity to the vaccine, because its genetic code will have changed enough. That's why we want to study the dynamical and mechanochemical processes that fuel the polymerase's operation and its propensity to make mistakes. We don't want to repair the car taking a picture of the wheels. We want to open the hood, see the engine, and get our hands dirty. We cannot use conventional biochemistry. I have spent 3 years studying the activity of one single molecule in real time using the optical juices technique. Now, we will see the experimental design we have developed. First, we covalently bind the viral complexes to a dielectric bead with 3 microns diameter in a biochemistry lab. We introduce them in aqueous solution, and all of this in a macrofluidic chamber. The laser will trap the bead due to its geometry and dielectric composition. The beams will be refracted, producing a force competition whose resulting force will make the bead be stabilized. That's where the name of optical tweezers comes from. Now, we stay the bead still by section thanks to a micropipette that previously we made. We proceed trapping the next bead. The surface of this other one has to be functionalized just to bind the genetic material which is being synthesized by the motor. If moving away the beads we observe that there's a force against the movement, that means we have attached our complex. Finally, we can flow nucleotides to make polymerase begin the copy of the genome. If we keep a constant force and beads move away each other, we can conclude that polymerase is synthesizing material. Extracting a segment of a virus and isolate it in the optical tweezers device is a very complicated task. This challenge has taken more than 3 years. Finally, we reached the goal of isolating one single polymerase for the first time. Thanks to the optical tweezers, we can obtain information about the motor in real time. This novel single molecule method could mean alternative therapies which look for the solution in the origin. The RNA polymerase, the main responsible of the influenza's variability. In front of us, we have a bumpy road and a lot of measures still to do. But if we never give up, step by step we will be closer to defeat our enemy.